Okay. So today we'll talk about electric generators. We'll talk about transformers. So basically we'll get an overview of the whole power distribution system. But before we get there, we're going to talk a little bit about eddy currents, which is where we ended last time. Okay? And there's a really neat thing up here on the front. I would encourage all of you after class to come up and just try this out. And what we have is a very large magnet. Okay, it's just a sort of square magnet, pretty strong. And we have a very thick copper plate. Okay? And this really doesn't stick to the copper. Okay? However, if you move this over the copper, just above, I'm just putting it back and forth above, it feels like you're moving it through some really thick honey. Something really thick and viscous. And what's the explanation for that? Let's get some good thoughts on why that is. And then I can also drop it from like here and we can see what happens to it. And you expect a big clang when the thing runs into the copper, but what happens actually is... Isn't that cool? You like that, huh? Oh, he works once. No. Again, yeah, woo. So, what's up with that? Any thoughts on that? And you can kind of tip this over and watch how it falls. That's another neat thing to do. Just kind of tip it over, and it's going to fall down. But it just kind of falls over very softly. So, any thoughts on this? What does this have to do with what we've been talking about lately? Does it have anything to do with what we've been talking about lately? Anybody see a connection anywhere?
Like copper is like a...
Copper is a conductor. That's an important thing. Copper is a conductor.
And the magnet, you're like moving it around, so you're changing the...
I'm moving the magnet around, so I'm changing the flux through the copper.
So you're like creating an induced...
And so there's these induced eddy currents in there. Exactly right. Exactly. This sounds great. So changing the flux in various parts of the copper induces eddy currents. And the eddy currents, what they do, they create a field. Eddy currents are swirling currents of electrons. And they create a field which acts to oppose whatever's producing the change in flux. Well, what's producing the change in flux? The motion of the magnet, right? And so Lenz's law tells us that those currents act to produce a field that tries to stop whatever's producing the change in flux. In other words, tries to stop the magnet from moving. And that's what you feel. You feel this real resistance to motion. And honestly, you got to try this for yourself. Don't just believe me. Okay. Questions there? And so you can actually stop trains with this, right? As we talked about the other day. So we'll try and go over that. And again, I've got a very small version of this today. I had the very large version of this the other day. But we have a piece of aluminum, we have a magnetic field, and if the magnet's not there, then this acts pretty much like a nice pendulum, swinging back and forth. But if you swing it so that it ends up going through the magnetic field, it just stops dead. Okay? Doesn't actually physically make contact with the magnet. The magnet won't stick to the aluminum. Okay, it's not like steel or iron, but you get this neat effect that we call eddy currents. And then we saw the other day that if you cut these slots in the aluminum, that you can't get those big swirls. And so this one actually isn't nearly as affected. It's got almost as much aluminum as the first one, but it's not nearly as strongly affected as the first one because we've cut these slots in it and then we can't get these big swirling currents that set up the big fields that interact with the field of the magnet. Okay, so we're going to do our best to try and understand how train brakes work if they use eddy currents. Okay, so this brown circle here is one wheel on the train. And you really don't want the eddy currents to be on all the time, right? You don't want the train wheel to be trying to slow down all the time. So you don't use a permanent magnet, but you can use an electromagnet. So when the driver of the train presses the brake pedal, that actually switches on current to a coil, sets up a magnetic field. And the magnetic field is set up only in a small part of the wheel. You don't want to expose the entire wheel to the magnetic field because you need to exploit changing magnetic flux. Okay, if the whole wheel was exposed to the magnetic field and it was spinning around in that field, well, there would be no change in flux. So we're only going to turn on the field in this area here. Okay, so the whole wheel is spinning this way. And then I've got a couple of different regions colored here. This green region here is going to move in to this region of field. That's the difference between this picture and that picture. Some amount of time has gone by, enough time for this green region to move into the field, and then it's in the field. And this blue region has rotated out of the field. Okay? So the field's only on a small part of the wheel. The wheel's rotating clockwise, and we're going to move that green area into the field and just see what happens. Okay? So we've got a solid wheel, and then we turn on electromagnets, so magnetic field lines are passing through this region of the wheel, and we're trying to stop the train with this. Okay, so how is it done? So let's give that a shot. And so we can actually draw a set of before, after, and two opposed pictures for the green region. Okay, so here's the green region before it rotates in. There's the green region after it rotates in. Okay, so that's basically drawn the before and after pictures for you already for that green region. And that's just some small part of the wheel. We've just taken a green marker and drew a circle in green on the wheel. And we're going to see what happens. Okay, so what's your two opposed picture look like in the green region? Stuff going out. Okay. So we've gone from basically no field to lots of field lines going in. And so our two opposed pictures should have stuff coming out. And somebody asked about, what's going on with this process anyway. That was one of the comments basically on the pre-session quiz today. So what we're doing is we're saying in the before picture, we're drawing the field that this green thing's exposed to. I've drawn one field line. If you want to draw no field lines, that's fine. Doesn't really matter. The key is that after we've made a change, what's the change? We've rotated this wheel so this green region has come into the field. So after we made that change, there's more field lines. There's a change in magnetic flux. Flux, what is it again? Counting the number of field lines passing through the loop. That's all we're doing. So we got more field lines going through the loop in the after picture than beforehand. And then the two opposed picture, it's a two-step process there. First of all, you draw the field that the loop itself creates. And in this case, it creates it by running eddy currents around that region of the wheel. And the eddy currents in this, the field you need to create. So the first step in that process is say, okay, there's a change between here and here. To oppose that change, that part of the wheel actually runs an eddy current around itself to create this field here. So that's where you start in this picture. What direction is the field you need to basically, in some sense, add to this one to try and make it look more like this. Okay? And so we've added a lot of X's, field lines into the page. It tries to create field out of the page to oppose that change. And then you get your right hand, you say, okay, my thumb is my magnetic field. It's pointing out of the screen. And my fingers curl, and that shows me the way the current goes in that region of the wheel. Current going this way. Okay? Questions on that at all? Okay, so what impact does this have on the wheel? So now we have this swirling current. And so you might even want to just think about it here. Okay, so as this part of the wheel is rotating so that it's entering the field, we have a swirling current going which way? This way. Okay, this way around. Okay, as it's rotating in. And so what impact does that have? So we have a current and we have a magnetic field. And so we can get our right hands going and say, well, there's a force associated with that current acted upon by that field. Okay, which way is the force? And so your fingers now go in the direction of the current. So you got to pick a particular part of the loop to look at, right? So what part of the loop are we going to look at? Current at this point, this point, this point, this point. Where should we go? Any thoughts on that? So one thing to think about is the current has to be in the field, right? If we're really confining our field to this region here, well, the current out here, how much field is it feeling? None. So don't do it here, don't do it there, don't do it there. All those parts of this wheel are outside the field. So what really matters is the force we get here. Okay, so at that point, which way are we going? That way. So our current's basically in this direction. Our field is into the page. Which way is our force, according to our right-hand rule? Kind of down and to the left. Yeah, okay. Okay, and so kind of focusing on this region of the wheel, we get a force in this area down and to the left. Well, the wheel is rotating this way. If we get a force here, we're going to get a torque on the wheel, which is in what direction? Clockwise or counterclockwise? If we apply force in this direction at this point here, are we going to speed the wheel up or slow the wheel down? It's rotating this way. We're actually slowing it down with a counterclockwise torque. Okay, so that's how it works. And you can do the same analysis on the blue region. Okay, as the blue region spins out of the field, you get an induced current, and the interaction between that induced current and the magnetic field is such that it also tends to slow the wheel down. Okay, so feel free to try that out. Any? Yes?
I'm a little bit confused as to how the torque slowed, like what the relationship to the force is, like.
So force versus torque. Okay, so you're okay with me saying on this green region here, there's a force basically in this direction. Okay. Well, we're rotating around where? Center of the wheel? Okay. So we're rotating around the center of the wheel. We're putting a force on in this direction at this point here, this way. Is that going to make the wheel tend to go that way? Yes, it is, which is opposite to the way it's spinning already. So we're going to tend to slow it down. Okay? And faster the wheel is spinning, the bigger the force is, because the bigger the current is, the faster the rate of change of flux. Okay? So you get this really nice smooth braking motion. As the train slows down, the force gradually decreases till you come to a nice stop. Okay there? Okay, so that's the basics of how train wheels work. Okay, so what did we just say? Electromagnets turned on, passing a magnetic field through sections of the wheels, eddy current set up, act to slow the wheel down. All right then, so what if you reverse the direction of the magnetic field? So we just had the magnetic field going into the screen. We did that whole analysis. So now imagine the field is coming out of the screen instead. What is that going to do? Still slow the train down or speed the train up? Okay, so we're almost 50-50. Okay, so let's go back and take a quick look at our picture, okay? So let's go back and look at that. So if this came out instead, the field would be in the opposite direction. And we could do the analysis. And this would have dots on it. This would have more dots on it. And that would have X's on it. And if this has X's on it, what does the current do? It goes the other way. So not only do we reverse the field, that also causes the currents to swirl in the opposite direction. Okay, so when you get your right hand going, if you only reverse one of those things, current or field, then your right hand's going to get a force that goes in the whole opposite direction as it did before. But if you reverse both of them, the field and the current, it's like taking a negative and a negative. What do you end up with? Exactly where you started. You're always going to get a force that tends to oppose whatever's producing the change in flux, and that's the motion of the wheel. Okay, so feel free to try the whole analysis again, but what you're going to find is a force going exactly the same way, because the current in this area is going to be going the other way, and the field lines are coming out of the page. You do your right-hand rule, that's the force direction again. Still acts to slow the wheel down. Okay, and this is what Lenz's Law is all about. Okay, you're always going to get resistance to whatever's causing the flux to change. Okay, you can't use this to put energy into the system. It's great for taking mechanical energy out of a system, but you can't use it to go the other way. Are we okay with that? Okay. And like when you want to stop the train, this is a great thing, okay? You actually physically make a brake, you exploit eddy currents to get rid of this mechanical energy. Sometimes you want to eliminate eddy currents. You want to do whatever you can to eliminate eddy currents because they just lose energy. So power companies, actually in the whole power distribution process, do whatever they can to get rid of eddy currents, okay? So in the train situation, it's a good thing to get rid of that energy. That's exactly what you want to do, stop the train. But in other cases, you're generating electricity, you're trying to get it 500 kilometers away to power somebody's computer or whatever, then you don't want that energy to get lost. So we'll talk some more about that as we go through today. Okay, any other questions on eddy currents? Okay. Okay, so let's move on to generators. And the whole pre-session quiz was about generators, so you guys are experts on generators now, so I'm not going to spend too much time on them, but we'll go over some of the basic ideas, and this was in the movie. So we've done motors before, and motors are ways to transform electricity, electrical energy, into mechanical energy, motion. And the generator does the exact opposite. You make something move, and you tap that motion to generate electricity by exploiting Faraday's law, changing flux, things like that. And the neat thing is you can use basically the same device to do both jobs, okay? And so basically at the heart of both things are just a loop and a magnetic field. And in the top picture, we're putting electrical energy in that's being supplied by the battery and electricity running through that loop. Then we've got current in a magnetic field. We get forces that give rise to torques that make the loop spin. And we've got our split ring commutator that keeps the torque always going the same direction. Okay? So even when you split, so B, the picture is the loop has actually gone through 180 degrees, but the torque is still going the same way. Okay, so you have to modify a little bit your connections here to the loop when you use it as a generator, but it's really at the heart the same thing, same loop in the same magnetic field. And what we're going to do now is we're going to maybe attach that to some kind of crank, and we're going to physically crank that thing, or we're going to have a dam with just tons and tons of water running through a pipe, and that's what's going to crank the loop. And we're going to spin the loop, and that changes the flux through the loop, and that generates electricity, and we can light up a light bulb, or we can light up the city of Boston, or whatever. It depends how big this thing is. Okay? And just so I can prove for you that we really can use exactly the same device as either a motor or a generator, I will do that. Okay, so I have this little device here. It's got a little crank on the end. That's not me, that's this thing here, this white thing, that's the crank. Okay, so, and I'm going to spin the crank, and it's connected to the light bulb. Okay, so if it's going to work right, then, let me put it over here so it catches it on there. So if it works, then it lights up the light bulb. Did it light the light bulb up? But only while it was spinning, right? If I stop spinning, it stops. If I keep cranking, it goes. Okay. So I just use this as what? Generator. I generate electricity. We proved that by lighting up the light bulb. So this was just acting as a generator. Now I'm going to put it down on the table and make it act like a motor. And I can't do it with the light bulb, right? So what I'm going to do is take its twin brother, identical one, and use this one as the generator and connect it up with this one and use this one as the motor. Okay, so I'm going to feed electrical energy in by turning the crank here, and what's going to happen on this end? Right, it's going to spin. Okay, so that's the idea. Ready? Here we go. Okay, so it kind of acts like this demented one-legged crab just crawling around the table. You know, but, and if I reverse the way I go, it reverses the way it goes. Okay? Woo! Ah, there it goes. Okay, so you really can use the same thing as a motor or a generator. Okay? Questions there? Okay. And so, you saw this on the movie if you watched the movie. there was an animation of this, and I'll show you that again in a couple of minutes. So if the loop spins, here's the loop. And again, as I mentioned on the movie, I'm not showing what this is connected to, but this could be connected to A, a light bulb, or B, the entire city of Boston, depending on how big this thing really is. Okay, but it's connected to something, so we really do have a complete circuit, and we're going to get current to flow when we change this. Okay, so we're going to fix the magnetic field, then we're going to rotate the loop. And if we rotate it so that the flux decreases through the loop, in what direction is the induced current going to be? Okay, so try that out. And I really encourage you to draw the 3 pictures, before, after, to oppose, and answer it this way. Okay, and this might be one of our very last chances. This could be the last chance to do this together in class. So really work on it. Let's get it right. Let's get 100% right. What do you think? Oh, just got it. Anybody else want to get their answer in? Last 10 seconds? Okay, we're going for 100%. Getting the right answer, right? Awesome. Okay. Okay, well, you know, we're getting there. We're getting there, 70%. So what about answer 3? Will there be an induced current? Sure. Why? The whole thing about induced current is you need to change the flux, and as long as you have a complete circuit, and it doesn't look like I had, but I made that argument that I really did. You know, I just not showing the light bulb or the city of Boston or whatever. But there is a complete circuit. We are changing the flux. We'll get a voltage. Because we have a complete circuit, we therefore get a current. There will be a current. Okay, so this is basically the before picture right here, right? So when you draw the 3 pictures, you start with the before picture. That's where we started. So we rotate this, and then there's fewer field lines passing through the loop. Okay, the loop actually has the same area. Doesn't look like it because we're looking at it, you know, side on, but it's rotating kind of so it's more getting close to being edge on with us. But it's the orientation between the area vector and the loop that we've changed. So, but we've got less flux, fewer field lines here than here. Are we okay with that? So the to oppose picture, should it have X's on it or dots on it? Should have X's. What have we done between before and after? We've taken X's away. We've taken field lines away that were going through the loop into the page. There's fewer over there. So the loop tries to bring them back. Okay? And it tries to bring them back by running a current around itself. And if we need X's on the to oppose picture, then your thumb is your magnetic field created by the current. These fields are created by something external to the loop itself, but this one is created by the current in the loop itself. And so your thumb is the magnetic field into the page, and that must be created by a current that goes clockwise. Okay. Which I hope was the 71% rather than the other one. Was it? Oh, that's good. Good. Okay. Any questions on this at all? See what you do with this question. So, as the loop rotates, think about how the current behaves as a function of time. So I'm asking you, what instant is the magnitude of the current maximum? Choose the best of those 3 answers. And which answer corresponds to the picture, actually? The first one, right? Yes. So the plane of the loop is perpendicular to the field. That's as shown here. Plane of the loop is parallel to the field. Then the loop will have rotated from this orientation to this orientation. Okay, it would just look like a line to you. And then there's an answer 3 as well. Okay, so see what you like from those answers. Okay. And so there was an animation of this on the movie, if you've watched the movie. And so let's try this out. On the worksheet, it says, sketch a graph of the magnetic flux through the loop as a function of time. Okay, try that out. We're going to assume the loop is rotating at a constant rate, constant angular speed. So sketch a graph of magnetic flux through the loop as a function of time. Remember, we define positive as meaning field lines going through the loop in one direction, negative is going the other direction. And this is from the loop's perspective. Okay, so for instance, if I define, the side of my worksheet that says electric generators and transformers now has field lines going from this side of it and out the back, right? But if I rotate the loop, the side that has electric generators and transformers on it has field lines coming the whole opposite direction. Okay? So from our point of view, the field lines haven't changed. But from the loop's perspective, when you rotate it 180 degrees, the field lines are going through the loop in the opposite direction they were before, from the loop's perspective. Are we okay with that? Yeah? Okay. Okay, so what do your graphs look like? Oh, that's beautiful. You've drawn a beautiful cosine. Okay. Did you watch the movie? Good. Okay. So, beautiful cosine. Who likes that? Beautiful cosine graph. Anybody else? Yes? Yes? Anybody else get something else? Okay. So if the flux is a beautiful cosine, which I kind of like the sound of that, draw another graph. Remember that the induced current is proportional to the negative of the slope of the flux versus time graph. Try and use that to help you sketch a second graph, which is the induced current as a function of time graph. Okay, so there's my flux graph. It's also a beautiful cosine. Okay, so does this have a constant slope? Would you say this has a constant slope, this graph? No? Okay. If it did have a constant slope, then there'd be a constant current. Because it doesn't have a constant slope, the current is not constant. How about the sign of the slope? Sometimes it's positive, sometimes it's negative. Once in a while it's even zero, isn't it? Mm-hmm. Okay. So can you go from there to your current graph? And when is the flux constant? Remember we had our field lines going through the screen, into the screen. If I hold my loop up here, this was answer 1, right? The loop was this way. And answer 2 was the loop is this way. So in which case do I have maximum flux? This, right? When the field lines are going through and I hold my loop this way, that's maximum flux. If I hold my loop this way, it rotates 90 degrees, so it's this way, no flux at all. The field lines are going over and under. Okay? So this one was answer 2, this was answer 1. We've ruled out answer 3. Current, what does your current graph look like? It's a sine wave when the other one's a cosine. Okay. Do we buy that? Let's see. Sine graph starts at 0. What's the slope at the very top of the cosine? 0. 0. Okay, it starts at 0. And then the slope is negative. But you had your graph going positive, right? But the slope is negative. Does that mean the current is positive? Oh, right, it's proportional to the negative of the slope. So if the slope is negative, there's another minus sign, it's positive. Exactly right. Okay. So you, in fact, do get, here we go. Okay, so flux is black. The purple one is the current. Okay, so when do you get maximum current? Let's look at that again. Okay, oops, we'll reset that twice. Here we go. So here we go. We'll step through this. Okay, so the flux was maximum to start with. The current was 0. The current's, oh my goodness, current's 0 now. Sorry, current's maximum now. Which way is the loop? It's this way. Which answer was that? That was answer 2. Okay. So why is that? Because when it's in this orientation, in fact, the current is 0, because as it passes through that orientation, as it's rotating, it's basically just not changing area there or not changing flux there just for an instant. It's reached the peak of the flux graph. Okay? But here, as it passes through this orientation, you're basically changing from field lines going one way through the loop to field lines coming the opposite direction through the loop. You're actually changing the flux most quickly at that orientation. Okay? So that's why you get it there. So in fact, the flux is actually 0 there, right? But the change in flux, that's the key, is the highest you get. So strangely enough, it's where the flux is 0 that you get the peak current, because you're changing the flux most quickly. Bless you. Questions on that? But if you can see what's going on in these graphs, okay, you can get it out of the graphs. Okay. You okay there? All right. How about this? On the very bottom of that page, it says, because there's a current going through the loop, we just generated one, the loop experiences a torque, because now we have a current, induced current in the loop, and it's in a magnetic field. There's a torque on the loop. Okay? What does that torque tend to do? The torque acting on the induced current. So you're actually cranking away like crazy, making this thing spin. And so there's one torque. You're making it spin in the first place. But there's a torque associated with the induced current interacting with the field. Do you think that helps you? It acts the same direction you're going? No? Because the Lenz's law says this induced current is going to do what? Oppose the thing that's making the flux change. What's making the flux change? You cranking the thing, right? So it's actually going to put on a torque that makes it harder for you to spin it. Okay? And you can feel that. If you actually spin this thing, connect it to the light bulb, and spin this, it's actually harder to spin when you're hooked up to the light bulb than when you're not. Because if you're not, there's no current. And there's none of this counter torque. Okay, so you saw all this on the pre-session quiz. So let me just talk briefly about the pre-session quiz. It's all about this, right? It's all about women's basketball. But that is an omega, not a W, okay? So just remember that. So on the pre-session quiz, what we do? We gave you omega, we gave you N, we gave you B, and we didn't quite give you A. That was one problem that some people had, is I think you just assumed it was A, but it wasn't A, right? So we actually gave you the length of the square thing. So what do? You got a square thing, you got a length here, you got another length there. Multiply those together. And also there it was given in centimeters, right? So you got to convert to meters. So don't forget that it's length that we gave you in the pre-session quiz, and it's area in the equation, and convert to meters. Okay? And then I had a nice conversation in office hours with somebody today, and they came in and they said, look, I got this humongous answer for omega. When I calculated omega, it was enormous. There's no way it can possibly be right. Which was actually the entire point of the pre-session quiz. Well, one of the points of the pre-session quiz, right? It was huge. When you get to revolutions per minute, it's like 2 million revolutions per minute. You got to spin this thing to generate a decent amount of voltage. Which is why no electricity generating plant makes use of the Earth's magnetic field to generate electricity, right? That's what we were doing in the pre-session quiz. It's just not even close to being big enough. Okay? You just got to get permanent magnets that generate a nice strong field way bigger than the Earth's magnetic field, and then you can have, in fact, you have to rotate if you're in North America, you have to rotate at 60 hertz. Okay, 60 times a second. You can't go 2 million times per minute. You actually have to go 60 times per second because that's the frequency you need to come out of your wall socket. So omega is actually fixed, and then you can figure out what you need if you want to generate 170 volts or 2 million volts or whatever. Okay? But yeah, but that was a ridiculously large number, and you're absolutely right. But that's because the field strength of the Earth is really very small. Too small to do anything useful, really, in electricity generation. Okay, any other questions on the pre-session quiz or this equation or anything? There's one. How do you do the RPM calculation? Okay, so you're okay with getting omega in radians per second? Okay, so then you just got to convert from radians per second to revolutions per minute. So there's two conversions there. One is to go from seconds to minutes. That's a factor of 60, right? Not 3,600. I think some people actually make that mistake, but it's just 60. We're not going all the way to hours, just to minutes. Okay, and then you got to go from radians to revolutions. And in one revolution, how many radians are there? 2 pi, exactly right. So you take your omega in radians per second, divide by 2 pi to get to revolutions per second multiplied by 60. So you end up multiplying by 60 divided by 2 pi. Okay. Okay, so then we get something called back EMF, which I'll talk briefly about. And you probably noticed this in your house, especially in the summertime. And if your house is really old, it happens a lot. But you turn something on, maybe your hair dryer does this. Some people's hair dryers do this in their apartments because hair dryers draw a lot of current. But you turn something on, draws a lot of current in your house, and the lights dim. Or in the summer, air conditioner comes on. Air conditioners, right when they turn on, draw a lot of current. Okay? So they draw so much current that it basically affects everything else in the house, and the lights dim for just a couple of seconds, then they come back up. Okay? And so what happens here is anything that has a motor in it, like a compressor in a fridge or a compressor in an air conditioner is a good example. Okay? What does the motor need to do when it turns on? It spins, and it's a coil in a magnetic field. So what does a coil do in a magnetic field? It generates its own voltage. Okay? So a motor, just by its very nature, when it's on, when it's operating, spinning, actually also acts like a generator at the same time. Can't get around that. Okay? And that generated voltage always opposes the voltage that's trying to make the thing spin in the first place. This is why we call it a back EMF, a voltage that acts against the thing that's making the motor spin in the first place. And because these voltages are basically in opposite polarities, you get a reduced current. It's like having two batteries, one hooked one way, one the other way, and the current overall is reduced. So at the very beginning, when the motor first turns on, you don't have any of this back EMF because the thing's not spinning. So you draw an incredible amount of current, lots of current. And then when you get it up to operating speed, you actually have much less current because of this voltage generated by the motor itself. Okay, so we'll just go through a quick calculation, just a simple example calculation of this. Okay, so our applied voltage is delta V. We've got some resistance in our coils in the motor with R. And so here's Ohm's law. Remember Ohm's law? And let's do an example. Wall socket voltage, 120 volts. Our resistance in our coils is 6 ohms, 20 amps. You first turn on your motor, you get 20 amps of current. Okay, that's a fair bit of current. And in fact, it is enough to dim your lights slightly in some houses anyway. And then, let's say that when the motor's up to operating speed, it doesn't take too long to get there, you know, a couple of seconds, we generate 108 volts of back EMF. Okay? So then it's like 120 volt battery hooked one way, 108 volt battery hooked in the opposite direction. We have a net of just 12 volts there. And so our current is 2 amps. And so we need lots of current to get the thing started. But once we have it rotating at its operating speed, the 2 amps is just needed to overcome friction and things like that, and actually do some work as well. Okay, so you start with lots of current, your lights dim, but then you're up to operating speed on your motor, and your current is actually much, much less. So all your lights come back up again. Are we okay with that? And again, we see Lenz's law coming into play because this is a voltage that acts, it's got the opposite polarity of the voltage driving the motor in the first place. Okay. Okay. Okay, so let me get to transformers. We got 6 minutes for that. Okay, so transformer is, you know, you got them all over the place. You probably have 7 of them that you physically own yourself. Cell phone charger, adapter for a battery, you know, any of those big brick things you plug into the wall socket. And your computer or your cell phone doesn't like 120 volts. It's actually plus 170 volts down to minus 170 volts, oscillating that through that cycle 60 times a second. A lot of your electronic devices don't like that at all. Okay, so you transform that ultimately into, you know, 9 volts DC or whatever. And this is part of the process. This does not do AC to DC. This actually does AC to AC at a different voltage, and then there's another step down the line where you convert that AC of a lower voltage, or a higher voltage in some cases, into direct current. We're not going to talk about that part. But it's a pretty simple system. You run alternating current through this coil. Okay? Well, current through a coil generates what? Magnetic field. Magnetic field. And Then you wrap it around this piece of iron, and the iron basically A, magnifies the field, and B, funnels the magnetic field lines over here, passing them through the secondary coil. Okay, so you're generating magnetic field here, and it's changing magnetic field because this is alternating current. And you funnel all those magnetic field lines over to here, and they're changing magnetic field. Sometimes they're doing this, sometimes they're going this way. Steadily changing magnetic flux through the coil is going to generate a voltage over here. We'll get a current over here. Okay? And there's a nice relationship between the voltage and current on the two sides. Okay, so we're exposing both coils to the same changing flux. We're approximating here. We're going to lose a few of the field lines. You know, some of the field lines we generate over here are not all going to pass over here, but let's say we get 99.9%. Let's call it 100%. Let's just assume we get all of it over there. So if you expose them to the same change in magnetic flux, that looks different from Faraday's law, but it's Faraday's law. Okay? Minus, there's an N, there's a voltage, there's a delta flux over delta T. It's Faraday's law. Okay? And so you can say delta V, the voltage across the primary, divided by the number of turns in the primary, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay, number of turns, is the same ratio for the secondary. That's the other coil. And then the other thing we can do is say we're going to conserve energy here. And so our input power, voltage times current in the primary, has to be voltage times current in the secondary. Again, that's a bit of an approximation too, but not too bad most of the time. And so here's our basic ideal transformer equation. Okay? Ratio of the number of turns is the ratio of the voltages, is the inverse ratio of the currents. Okay? Primary, primary, secondary, 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 primary. Okay? And so the bottom line is, in this case, the number of turns is bigger over here than over here. Okay? So if the number of turns goes down, the voltage goes down. But if the voltage goes down, something goes up to compensate for that, and the thing that goes up is the current. Exactly right. Voltage goes down by a factor of 10, current goes up by a factor of 10. Okay? Okay. So I brought a little model of a transformer here. Two coils hooked up by this iron core. Now this iron core, interestingly enough, is it one big solid piece of iron. In fact, what it is about 20 laminated sheets. Okay, so you get 20 laminated sheets all going this way, stacked on top of each other. Why would you do that instead of having a nice, just solid piece of iron? Think about where we started today. What did we start talking about? Exactly right. It's all about eddy currents. Okay, so the laminations do what, where did it go? This one. Do what the slots do in this, right? The laminations prevent big swirling eddy currents that would reduce all the energy. You could dissipate all sorts of heat, thermal energy, in here if you allow those big eddy currents to swirl. So you get rid of those eddy currents by this. And for a power company, you know, power is money, right? So they do whatever they can to eliminate any losses. Okay, so let's try this out. Transformers are designed to work with alternating current. Okay, they're not designed to work with direct current. But we're going to, just for fun, try it out with direct current. Okay, we got a battery, 12-volt battery over here. We're going to close the switch. Does the resistor notice anything on the other side? Okay, so what do you think is the best answer to this question? When we close the switch, what about the current through that resistor on the other side? Okay, and then we'll stop there and we'll come back on Friday. Okay, so this is all about flux, right? So if the switch is open, how much flux do we have passing through our secondary coil? None, right? Because there's no current, there's no magnetic field, there's no flux. Okay. When you close the switch, then you get a current through the coil, then you get a flux, right? You get a flux because you get a field. But you're going to argue with me that it's not a what kind of flux? It's not
It's not changing.
It's not changing. So it only changes just briefly, doesn't it? You go from no flux to steady flux. So during that brief period when you're closing the switch, there's a small time interval during which the flux changes. So what's the best answer? Brief current. I like 4. Okay? There's a brief current, and then the current goes to 0. So only while the flux changes you get any current. Okay, so we'll see you on Friday.